Hello everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and introduce a very important mechanism known as an infinite series. So what is exactly an infinite series? So we're going to begin with a real valued sequence, so we're going to be calling that sequence AM, and we're going to define a mechanism known as a partial sum. So we're going to define this sequence Sn, which is going to be the sum of the first n terms of a real valued sequence an, which some people write as this little finite sum, the sum from k is equal to n of ak. Then the pair of sequences an and Sn is what is called actually an infinite series, and Sn usually is called the partial sum or the nth partial sum of that series. So let's just do a quick example of what exactly a series is. So we're going to define our sequence an to be equal to n, and n is obviously going to be instead of natural numbers. Therefore, what is the nth partial sum of this sequence? So this is going to be equal to 1 plus 2 plus 3 all the way up to m. And we already know that this is going to be equal to n times n plus 1 divided by 2. So that means that the pair n and then n times n plus 1 divided by 2. So here is our sequence. Here is our nth partial sum. This pair from n is equal to 1 to infinity is an infinite series. Right? So this is what we refer to as an infinite series. Now, most of the time, if I give you an arbitrary sequence, obtaining the closed form of the nth partial sum isn't always the easiest. So that's sort of where the other theorems of infinite series sort of come into the picture, because getting this closed form is usually not too easy. So once we have our infinite series, now what can we do with it? So that's where this next definition is going to come into the picture. So the infinite series, am Sn from n is equal to 1 to infinity converges to S. Obviously this, when we say convergent, we mean convergent to a real number, provided that the limits of the sequence Sn, let's call that limit S, belongs to the set of real numbers. And if it does, we will write this as the sum from k is equal to 1 to infinity of ak, our baby sequence, and we're going to say that that's equal to the limit of the partial sum, right? So we can write this equivalently as the limits as n goes to infinity of the sum from k is equal to 1 to n of ak, right? And that little thing should be equal to n. So the limit of an infinite series, or the value of an infinite series, is just the limit of the partial sums Sn. So that's equal to the limit of Sn. Okay, so that's a couple different ways of writing the limit of an infinite series, provided that it even exists. So if we go back to our example that we talked about earlier, so our partial sum of the first consecutive natural numbers was equal to n times n plus 1 over 2. But what do we know about this particular sequence? So this sequence actually, can easily be proven that is not bounded above. And we also can show that it is a monotonically increasing sequence. So we have a monotonically increasing sequence that's not bounded above. So that means that the limits of Sn does not belong to infinity, i.e. the sequence diverges. So if the limit of the partial sums does not belong to the set of real numbers, that means the sum from k is equal to 1 to m of ak as n goes to infinity, so let's just replace n to infinity, this series diverges. Right? So that's practically what we're going to be doing today. We're going to be looking at several different series and analyzing their convergence or potential divergence. So the sum of consecutive natural numbers obviously is a trivial case, because in some sense it grows and grows and grows. But just because it grows and grows and grows does not necessarily mean that sum doesn't converge to something. So let's look at another very famous example, and this example is known as the harmonic series. The harmonic series. So what exactly is a harmonic series? So define an to be equal to 1 over m, where n is a natural number, and therefore the nth partial sum is going to be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, all the way down to 1 over n, which we can write in more compact form as the sum from k is equal to m of 1 over k. So it's just the sum of unit fractions from 1 over 1 to 1 over n. And some people will call this the nth harmonic number as well. So our question that we seek to answer is, does the limits of this partial sum belong to R? And if it does, that means that is the value of the associated infinite series, right? So let's assume it does. So let's assume it does. So obviously if I'm going with a let's assume it does converge, that's probably implying that I'm going to go for maybe a contradiction, implying that it actually does not converge. So if it does converge, then we're going to call the sum from k is equal to 1 to infinity of 1 over k, we're going to call this L, and L is going to belong to the set of real numbers. So that means what? So that means that L must be equal to 1 plus 1 half plus 1 third plus 1 fourth plus 1 fifth plus 1 sixth plus 1 seventh plus 1 eighth, and so on. So that goes on forever. And now what I'm going to do is I'm going to sort of combine or change up the values of 1 over 3, 1 over 5, 1 over 7, and all of the odd terms, right? So if it's equal to an odd number, so if it's equal to, say, 2k plus 1, where k is an integer, I'm going to shift this up to 2k plus 2, right? So if that is the case, that means 1 over 3, for example, is going to be equal to 1 over 4. We're also going to have like 1 over 5 is going to be greater than 1 over 6. So we're going to be creating a comparison to a different sequence. So this is going to be greater than 1 plus 1 half. 1 over 3 is an odd number, so I'm going to change that to 1 over 4. We still have that 1 over 4 there. That 1 over 5 is going to shift up to 1 over 6. That 1 over 7 is going to shift up to 1 over 8, and so on. And what we have here is repeated terms in groupings of 2, right? So that's 2 fourths, that's 2 sixths, that's 2 eighths, and then we're going to have 2 tenths, 2 twelfths, and so on. So if I reduce 2 fourths, I get 1 half. If I reduce 2 sixths, I get 1 third. If I reduce 2 eighths, I get 1 fourth, and so on. So this is going to be equal to 1 plus 1 half plus 1 half plus 1 third plus 1 fourth plus 1 fifth plus 1 sixth, and so on. So if you notice that if I sort of ignore this particular 1 half, the rest of it is the same harmonic series. So what I have here is that L is greater than, and we have that 1 half there, plus L. Right? So we have this little series sequence there. So what does that exactly mean? So we have that L is greater than 1 half plus L. So if I subtract L from both sides, because L is just a real number, we have that 0 is greater than 1 half, and that's obviously a contradiction. So that means that the sum from k is equal to 1 to m of 1 over k, i.e. the harmonic series, does not converge to a real number, right? So that's actually pretty interesting. So we have a sequence that does converge to 0 as k goes to infinity, but those partial sums do not necessarily converge to a real number. Now let's take a look at a couple other infinite series. And for example, 1 over k times k plus 1 on the bottom. So obviously all the terms on the bottom are positive, so this is growing as well, similar to the harmonic series. But does it converge to a real number? So as usual, we have that the bottom is converging to 0, but that doesn't necessarily imply that this series converges, okay? Because we have a harmonic series as a counterexample to that. So the first thing I want to notice for this particular infinite series is because we have a product of two polynomials on the bottom, so we can also always use partial fraction decomposition on that fraction. So we're going to have the sum from k is equal to 1 to infinity of some number over k plus some other number over k plus 1. And we just need to figure out what those things need to be. So we know that that 1 over k times k plus 1 must be equal to a over k plus b over k plus 1. And if we cross multiply by k times k plus 1, you get a system of equations. In particular, 1 is equal to a times k plus 1, and then plus b times k. So if we let k be equal to 0, and also k to be equal to negative 1, you're going to find that a must be equal to positive 1. And you're also going to find that b must be equal to negative 1. And once you have that, that means we can re-represent this infinite series as the sum from k is equal to 1 to infinity of 1 over k minus 1 over k plus 1. Right? So if we look at the partial sum of this infinite series, what exactly are we going to have? So Sn is going to be equal to what? So the first term is going to be equal to 1 over 1 minus 1 over 2. And then the next term is going to be 1 over 2 minus 1 over 3. Minus 1 over 3. And then we're going to have 1 over 3 minus 1 over 4 plus all the way down to 1 over n minus 1 over n plus 1. So if you look here, notice that minus 1/2 and 1/2 are opposite signs, so they will cancel out. If you look at the next two terms, we have minus 1/3 and 1/3, they're going to cancel out. The next term is going to be minus 1/4 and 1/4, they're going to cancel out. And eventually, if we can continue this pattern, 1 over n is going to cancel out with the term that comes before it. So what we're just going to be left with is the very first term in the pair and the very last term in the last pair. So we can clearly see that the partial sum is equal to 1 minus 1 over n plus 1. So that is the sequence, and obviously we can take the limit of that sequence. So that means the limit of the partial sum, 1 minus 1 over n plus 1. We already know that 1 over n plus 1 converges to 0, so we know that this limit is just going to be equal to 1. So that's the limit of the partial sum. So that means the sum from k is equal to 1 to infinity of 1 over k times k plus 1 converges to 1. So that's actually a very nice series. So just because the sequence an converges to 0 does not necessarily imply its convergence, but we have that if since the bottom grows super fast or fast enough, then it probably or likely will converge. So let's look at another fun example. So let's throw in some negative numbers. So let's do the sum from k is equal to infinity of minus 1 to the k. So this is going to be equal to what? This is going to be equal to minus 1 plus 1 plus minus 1 plus 1 plus minus 1 plus 1 and so on. So it's going to alternate. So notice here that this is going to be our n is equal to 1 term. This is going to be our n is equal to 2 term. This is going to be our n is equal to 3 term. This is going to be our n is equal to 4 term, and so on. So all of our odd terms are going to be equal to minus 1. All of our even terms are going to be equal to positive 1. So if we look at our partial sum sequence, what are we going to have? So when n is equal to 1, we have minus 1. When n is equal to 2, we have minus 1 plus 1, which is going to be equal to 0. And then the next term, when we add negative 1 to 0, we're going to have minus 1. And then we're going to have 0, then minus 1, then 0, then minus 1, and then 0, and it's going to alternate. So our goal is, does the limit of Sn belong to R? If so, the limit is equal to the value of this infinite series. So, does it converge? So keep in mind, Sn is just a sequence, and if we analyze any two subsequences, for example S2n, if we focus on the even terms, we clearly see that the limit of S2n is going to be equal to 0, and the limit of S2n minus 1 is going to be equal to minus 1. And since we have two subsequences that converge to different limits, then we have that the limit of Sn does not belong to R. Because if a sequence does exist, then any subsequence is also going to converge to the same exact limit. So if that is the case, that means the sum from k is equal to infinity of minus 1 to the k does not belong to the set of real numbers, and some people will say that this diverges. Right? So that's actually pretty exciting. So let's look at another, and actually very famous series. Let's look at a very general one. Let's assume that the absolute value of x is strictly less than 1. Then the sum from k is equal to 0. We don't have to always start at k is equal to 1. of x to the power of k, this is actually equal to 1 over 1 minus x. And also, if the absolute value of x is greater than or equal to 1, then the series diverges. Right? And some people refer to this as a geometric series. Right? So it's actually a family of series that converge as long as the absolute value of that base of that exponential function is less than 1. So anything from -1 to 1. Some people include 0, some people don't. But even if it is 0, you don't get any super big issues. So what we're going to do is we're going to prove the convergence case, and the divergence case you can easily get with a counterexample. So we'll leave that for you. So let's see if we can provide a proof for the convergence of an infinite series. So what we're going to do is we're going to look at Sn. So what is the partial sum of this? So the partial sum is going to be equal to 1 plus x squared all the way up to xn, where n obviously is greater than or equal to 0. And what I want to do is I want to multiply this entire series by x. So I'm going to have x times Sn. So that's going to be equal to x plus x squared plus x cubed all the way down to xm plus 1. And obviously still n is greater than or equal to 0 for that. So if I take these two finite numbers, I can subtract those two finite numbers, and that's going to give me Sn minus xSn. And that's going to give us what? So notice that we're going to have 1 minus x minus x squared minus x cubed. Since it's a finite number, I can rearrange it. And notice I'm going to have an x minus x, an x squared minus x squared, an x cubed minus x cubed, all the way down to xm minus xn. And that's just going to give us our 1 minus xm plus 1. Right? Now, let's assume, or actually since we're going for the convergence case, we're going to be assuming that x does not equal to 1. So I'm going to factor out Sn out of the left-hand side. So I'm going to have Sn times 1 minus x, and that's going to be equal to 1 minus x to the power of m plus 1. And then I can solve for my Sn, so I'm going to have Sn is equal to 1 minus x to the m plus 1 all over 1 minus x. So that is my partial sum. So now I just need to take the limit as n goes to infinity and see what this is equal to. So what I'm going to do is I'm going to break this fraction up into two fractions, and I'm going to call this Sn is equal to 1 over 1 minus x to the m plus 1 over 1 minus x. And if you look here, that's the claimed value of what the sequence converges to, and here's your sequence. So I'm just going to move that to the left-hand side and see if I can bound that above and then send that bound to 0. So that's going to give us the absolute value of Sm minus 1 over 1 minus x is going to be equal to the absolute value of the right-hand side. So that minus sign is going to be absolute valued. And then we're going to have x to the power of m plus 1, which keep in mind is just a positive number. But 1 minus x also is a positive number because we're assuming that x belongs to the interval minus 1 to 1 for convergence. So we're going to have 1 over 1 minus x times x to the power of m plus 1. And using some of the exercises that we did before, if x belongs to the power or interval minus 1 to 1, and we send n to infinity, this term is going to go to 0, regardless of what this real number in front is, right? So we have a real number times 0. That means this is going to be equal to 0 as n gets close to infinity. So that means that Sn minus 1 over 1 minus x, this distance goes to 0, which means that the limit of Sn is going to be equal to 1 over 1 minus x. And that's the value of the geometric series. And again, this is only true if x belongs to the interval minus 1 to 1, and if it's beyond this interval, the geometric series diverges, unfortunately. So the first important theorem that I want to introduce in terms of infinite series is the following. If your infinite series, the sum from n is equal to 1 to infinity, converges, then the limit of that an is equal to 0. The main point about this theorem is its converse, so that if the limit of that sequence is not equal to 0, then the infinite series is going to be a divergent infinite series. So this theorem is actually mainly focused on how to detect whether a sequence is divergent or not. So let's see. Let's see if we can prove this. So let's suppose that we have the sum from k is equal to 1 to infinity of ak. And let's assume that this is equal to the limit of its associated partial sum, Sm. And let's assume it's equal to L, and let's assume that L is in the world of real numbers. So we're assuming that this series converges. So let's list out, the partial sum Sn. So Sn is equal to A1 plus A2 all the way down to An. And then let's actually look at a different partial sum, Sn minus 1, which is just a subsequence of Sn. So Sn minus 1 is going to be equal to A1 plus A2 all the way down to Am minus 1. So that is my subsequence. And now, if I look at this, the only difference between these series, or these partial sums, is that An is missing from the right one. So if I look at the difference between them, I'm going to have Sn minus Sm minus 1 will be equal to just Am. So if I rearrange this and take the limit of both sides, then I'm going to have what? So I'm going to have the limit of Am will be equal to the limit of Sm minus the limit of Sm minus 1. We're assuming that the limit of Sn is equal to L, which is in the set of real numbers. So we're going to be assuming that the sequence converges. And if the sequence converges, then any other subsequence of that sequence will also converge to the same exact thing. So Sn converges to L, Sm minus 1 will also converge to L, and regardless of the value of L, L minus L will be equal to 0. So if that sequence converges, then the limit of that associated sequence that the sum is running over will always be equal to 0, provided that it does converge. Now, keep in mind, it's not necessarily true that it goes the other way. For example, if you remember, the sum from k is equal to 1 to infinity of 1 over k did not belong to the set of real numbers, but 1 over k definitely does go to 0 as k goes to infinity. So be very safe and not misuse this theorem. Right? So that's a very useful thing to keep in the back of your mind. So let's look at another very important function, actually. Let's introduce the Riemann zeta function. Some people will just call it the zeta function. So the Riemann zeta function. So what exactly is this? So the Riemann zeta function is going to be the function zeta of x is equal to the sum from k is equal to 1 to infinity of 1 over k to the power of x. So it's a function that's defined in terms of an infinite series. So the claim is that the Riemann zeta function is a real number as long as x is greater than 1. So if x is greater than 1, then this converges and is equal to what we call zeta of x. And the exact values of zeta x are not always easily representable, but as long as it converges, we can give it a name, let's say. So how are we going to prove that this indeed converges for x is bigger than 1? So let's look at a couple partial sums. So for example, the first partial sum is going to be equal to 1 over 1 to the power of x, which is just 1 over 1, which is 1. So that's what S1 is going to be. I'm going to skip S2, and I'm actually just going to jump up to S3, and you'll see why in just a moment. But this is going to be equal to 1 plus 1 over 2 to the power of x plus 1 over 3 to the power of x. And I'm going to use a comparison test like I did before with the harmonic series. And I'm going to shift 1 over 2 to the x up to 1 over 3 to the x, or vice versa. Depends on which direction you want to build this in. So what I'm going to do is I'm going to actually shift 1 over 3x down to 1 over 2x. So I'm going to have that that's strictly less than 1 over 2 to the x. Let's not forget our lonely little 1 in front. So we have 1 over 2 to the x, and then plus 1 over 2 to the x. Because 1 over 3 to the x is smaller than 1 over 2 to the x, so we get this particular thing. And that's obviously 1 plus 2 over 2 to the x, which is the same as 1 plus 1 over 2 to the x minus 1. So we have S3 is less than 1 plus 1 over 2 to the x minus 1. The next term I'm going to look at is not S4, S5, or S6. I'm going to actually be looking at S7. And you're like, okay, well, why are you looking at that? That'll become obvious in just a moment. So let's list out these first few terms. So 1 over 2x, 3x, 4x, 5x, 6x, and 7x. So if you notice here, 1, 2, 3 is our S3. And then we have these 4 terms here. And what I'm going to do, keep in mind we shifted 1 over 3 down to 1 over 2. We're going to be shifting 1 over 7, 1 over 6, 1 over 5. We're going to be shifting all of these down to 1 over 4. So if you sort of see, we're actually looking at powers of 2, right? Because this is 2 to the power of 1, this is 2 to the power of 2, the next will be 2 to the power of 3. Okay, so if I do that, that means this is going to be strictly less than what? So that's going to be equal to, so we're going to have this term here, so 1 plus 1 over 2 to the x minus 1, and then we're going to have the powers of 4, so that's going to be equal to plus 1 over 4 to the power of x minus 1. So if I do this again, what am I going to have? So that's going to be equal to S15, and that's going to be equal to 1 plus 1 over 2 to the x plus all the way down to 1 over 15 to the power of x, and that's going to be less than 1 plus 1 over 2 to the x minus 1 plus 1 over 4 to the x minus 1, and then it's going to be equal to what? Can you take a guess? I'll leave that for you to decide. So what are these indices exactly? So these nj's are going to be equal to 2 to the power of k minus 1, or 2 to the power of j minus 1, 2 to the power of j minus 1, where j is equal to 1, 2, 3, 4, and so on. So obviously we have that nj belongs to the set 1, 3, 7, and 15. So I'm looking at subsequences. Now what do we have? So if you look at this right-hand side, that's practically just a geometric series. So let's assume that y is equal to what's in common actually, because these are just powers of 2. So this is going to be equal to 1 over 2 to the power of x minus 1. And if, keep in mind, if x is bigger than, actually we don't want greater than 0, the domain is greater than 1. So if x is greater than 1, then what can you tell me about this value of y? You should be able to see that y is always going to be between 0 and 1 in this case. Right? So if that is the case, then what we have here is that, our partial sum, always positive, obviously. So Snj, that's our partial sum, is going to be less than 1 plus y squared plus y cubed, all the way down to plus y to the j minus 1. Right? Notice here that I'm missing our y to the power of j term. And so therefore this is not quite a geometric series. So that means it's going to be strictly less than the geometric series convergence value, because keep in mind y is between 0 and 1. So this is less than 1 over 1 minus the value of x, and this is a real number. So that means that's strictly less than infinity. So it converges. So that means that the limit, or 0 less than or equal to the limit of Snj, will always be less than or equal to 1 over 1 minus x, which obviously is in the reals. So that means what? So we have that the limit of this sequence is less than or equal to 1 over 1 minus x, and that's obviously true for all indices of s. So that means that the zeta function of x is going to belong to R for all x in the interval 1 to infinity. So if anybody says, what is the value of zeta 2? So zeta 2 in series form would be the sum from k is equal to 1 to infinity of 1 over k to the power of 2. So that's going to be equal to 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus and so on. So that's 1 over 1, 1 over 4, 1 over 9, 1 over 16, and so on. Some people will actually just call that zeta 2. And if you want the very cute value for this, hint, it actually has pi in it, which is actually pretty interesting. Then you have to use more advanced methods, of course. But if you don't know, you already know that this is just a zeta series of order 2, therefore you know it converges because 2 is bigger than 1. Therefore you can actually just call its value zeta of 2. So the proof of the convergence for the Riemann zeta function for x bigger than 1 actually indirectly uses something called the sequence comparison test. So what exactly does the sequence comparison test say? So let's assume that we have two sequences in the set of real numbers an and bn, and let's assume that bn is eventually larger than an for all n bigger than some natural number, capital M. So we don't require that an be less than or equal to bn for all natural numbers n, as long as it's eventually always bigger than an. That's all that matters here. Then, if the sum of bn, or the infinite series of bn, converges, so that means if bn converges, in terms of series, to a finite number, that means the series underneath it has to converge to a finite number too, because you can't have an infinite number less than a finite number. And similarly speaking, if you have an infinite number, i.e. an diverges in terms of its series, you can't have a finite number above it. So, if an diverges, that means the bn series is also going to be divergent as well. So I'm not going to get into the proof of that because it's actually pretty straightforward in terms of contradictions and those types of things. So this is called the sequence comparison test. But there's also another comparison test that doesn't look at the sequence directly, but it looks at the limits of them instead. So this is called the limit comparison test. Limit comparison test. So what's the difference between the sequence and the limit comparison test? So the limit comparison test says the following. So let's suppose that an and bn are real valued sequences with the restriction that they're always positive. So this is a very, very important assumption. So let's assume that the an and bn are always positive sequences. So if you have negative sequences, you cannot use the limit comparison test. So if this is the case, and let's also suppose that the limit of the quotient of the series an over bn is equal to r, and let's assume that this r is a real number. Okay? In particular, it's a non-negative real number, and one should be able to easily show that because an and bn are positive sequences. So if this is the case, what exactly do we have? Actually, we don't need to necessarily specify that, so let's drop it. So if that's the case, then what exactly do we have? So the first criteria of the limit comparison says the following. So if r does not equal to 0, then the series an converges if and only if the series, the sum of bn, converges. So if the limit of the quotient is equal to a non-zero real number, then if an converges, bn converges. If an diverges, bn diverges, and so on. And if r is equal to 0, then the series bn, if the series bn converges, and notice I'm focusing on bn, the bottom here, then the series an will also converge as well. So if the bottom converges, then the top converges under the r is equal to 0 case. So let's look at an actual example of how to use the limit comparison test, because this can get a little bit tricky if you're not comfortable with it. So let's consider the series S, which is equal to the sum from k is equal to 1 to infinity of 1 over the square root of k plus 1. And you might be thinking, well, can I use a comparison test for this? And you might be thinking, okay, well, maybe, because we know that that's going to be strictly less than the sum from k is equal to 1 to infinity of 1 over the square root of k. And we know that that's just going to be the Riemann zeta function evaluated at 1/2, and we know that's equal to positive infinity. But just because you have a series that's less than infinity, that doesn't imply that it's divergent. It doesn't even imply that it's convergent, because you could have an infinity that's less than that infinity too, right? So comparison test for the sequences doesn't actually get us anywhere for this particular example, right? So let's see if we can use the limit comparison test to get us something that's at least meaningful. So what I'm going to do is I'm actually going to use this 1 over square root of k sequence to my advantage, and I'm going to let that be my bk. So bk is going to be equal to 1 over the square root of k, and I'm going to let ak be equal to my original sequence. So I'm going to have this. So what I'm going to do is I'm going to look at the limit of the quotient of the sequence, ak over bk, which is equal to the limit of ak, which is going to be 1 over the square root of k plus 1, so that's going to be on the bottom, and then 1 over the square root of k, that's going to be put my square root of k on the top. So once I have that, I'm going to divide both sides by the square root of k. Keep in mind, k is never equal to 0 or negative 1, so there's nothing preventing us from doing this. So this is going to be equal to the limit of 1 over, so that's going to give us k over k plus 1 over k. So what's that going to be? So that's going to be equal to the limit of 1 over the square root of 1 plus 1 over k. Now, before moving forward, we already know that this sequence and its associated series diverges, right? So this diverges. So that means what in terms of AK, because AK is what we're actually interested in. So AK diverges if and only if this limit of AK over BK is not equal to 0. So when the limit of the quotient of the sequences is not equal to 0, then the convergence and divergence is biconditional between these sequences AK and BK. Okay, so what exactly does that give us? So once we take the limit of this actual sequence, that's going to give us 1 over 1 plus 0, which is equal to 1, which obviously does not equal to 0. So that means since BK diverges, so since R is equal to 1, which is greater than 0, and also since this sequence BK diverges, we have that AK also diverges. So that's how the limit comparison test works in comparison to the sequence comparison test. The next test that I want to introduce is sometimes referred to as the absolute convergence test. So let's suppose that the sum of the absolute value of AK is a real number. So the sum of the absolute value of our sequence converges, right? So this is usually what we refer to as AN is absolutely convergent, right? So absolute convergent, is that better than just basic convergence? Actually, yeah, because the theorem says if a sequence or if a series is absolutely convergent, then the associated series is convergent, right? So if it's absolutely convergent, then it's convergent. But keep in mind, if the series is convergent, that doesn't necessarily imply that it is absolutely convergent. So let's look at an example of how this absolute convergence test works. So example. So does the sum from k is equal to 1 to infinity of minus 1 to the power of k over k cubed converge? Yes or no? So let's look at the absolute value of our sequence. So what we're going to do is we're going to define AN to be equal to minus 1 to the k all over k cubed, which means that the absolute value of AK is going to be equal to 1 over k cubed. And that means the sum from k is equal to 1 to infinity of the absolute value of AK, which is just the sum from k is equal to 1 to infinity of 1 over k cubed, we know that's just equal to zeta of 3, which we already know is in the set of reals because 3 is bigger than 1. So we have that the absolute value of AK converges, which means that this series is absolutely convergent, which means that this series does converge, right? So by the absolute convergence test, or the ACT, we have that this series does converge. Now, just because it does converge does not necessarily mean we know what it converges to, but we definitely do have that the series does converge, right? And, find out what it does converge to is another world of difficulty usually on its own. So let's mention another theorem that I find very, very useful. And it's very similar to the alternating convergence or the absolute convergence test, and it's called the alternating series test. So alternating series test, or the AST compared to the ACT. Absolute convergence, alternating series, different ACs overall. And the alternating series test says the following. So let's suppose that AN, a subset of the real numbers, satisfies two properties. The first property is that the limit of an must be equal to 0, and b, a1 must be greater than or equal to a2, must be greater than or equal to a3, must be greater than or equal to so on. That is, this sequence is a monotonically decreasing sequence. So if we have a monotonically decreasing sequence, and it doesn't have to be strictly monotonically decreasing, and the limit being equal to 0, then the series, the sum from k is equal to infinity of minus 1 to the power of k of our little sequence ak, this will converge. This will converge. So with this alternating series test, I want to use it to introduce another very important function, and it's called the Dirichlet function. Dirichlet function. Dirichlet function. So it's sort of related to the Riemann zeta function, and here we have the Dirichlet function. So the Dirichlet function is defined as follows. So it's going to be eta of x is going to be equal to the sum from k is equal to 1 to infinity, minus 1 to the power of k minus 1. You could do k plus 1 if you want, but traditionally it's k minus 1, all over the power of kx. And this is going to be equal to, or in the set of real numbers, if x is bigger than 0. So you could look at the Dirichlet function as an alternating Riemann zeta function. So does this really converge for all x bigger than 0? So let's see if we can provide a nice little proof for the convergence of the Dirichlet function. So what we're going to do is we're going to let our ak be equal to 1 over k to the power of x, the non-alternating portion of this series. So if we have that x is a positive number, then you should be able to show that the limit of ak, i.e. the limit of 1 over kx, this is actually going to be equal to 0. So that's not a big problem. So if we want to use the alternating series test, we need to first make sure that the limit of the non-alternated portion goes to 0, and that it's also a monotonically decreasing sequence. So if we look at, for example, ak plus 1, which is going to be equal to 1 over k plus 1 to the power of x, by comparison, we know that this is strictly less than 1 over k to the power of x, and that's precisely equal to ak. So we have that ak plus 1 is less than ak, which means we have a monotonically decreasing sequence, and that's the second requirement for the alternating series test for it to work, right? So we have that for x is greater than 0, the limit is equal to 0, and notice that this is also true for x is greater than 0 as well. So by the alternating series test, that means that the eta function, or the Dirichlet eta function, converges provided x is bigger than 0. All right, so if you ever see one of these series, for example, if somebody says, what is the value of the Dirichlet eta function of 3, then that's going to be equal to the sum from k is equal to 1 to infinity of minus 1 to the k minus 1 divided by k to the power of 3, the alternating version of zeta of 3. And, one could ask, does this converge? And the answer is yes, because Dirichlet eta converges for x is greater than 0, and obviously 3 is greater than 0, so this is a real number. Now, what does this series converge to? Well, obviously, if I ask you this question, you could say that it's equal to Dirichlet eta of 3. But if I ask you what is the exact value of Dirichlet eta of 3, I'm probably asking, is it equal to like the square root of 2 over 3, or is it equal to pi over e? What is the cute value of the Dirichlet eta function? Right? So, those are always, nice questions to explore, but sometimes not the easiest to answer, right? So we have shown at least for these two functions, for example, zeta of x, we showed that this is a real number as long as x is bigger than 1, and we showed that the Dirichlet eta function is a real number as long as x is greater than 0. So it's at least defined on these intervals. So here's a nice little question for you to explore, especially if you know about continuity, and that's the following. So is the Riemann zeta function continuous? So is the Riemann zeta function continuous on the open interval 1 to infinity, and is the Dirichlet eta function a continuous function on the open interval 0 to infinity? And if you're feeling very adventurous, I invite you to test whether these functions are uniformly continuous, Lipschitz continuous on those domains or not. Right? So those are just some very basic and fundamental properties associated to infinite series that you definitely should know. Hope you enjoyed this video, and I'll see you in the next one. Take care.